Hey guys, what's going on? So today we are going to be talking about two derivations of the geodesic equation. We're going to go through a Lagrangian approach and somewhat of a more simple approach. I'm going to do the simpler approach first, then I'm going to pursue the Lagrangian approach. The idea here, again, is that geodesics is really where the physics is going to be. I'm going to focus a lot on geodesics. After this, we're going to take a look at the relevant tensors, the Weil tensor, the Riemann tensor, the Ricci tensor, and all those tensors before we dive into deriving some interesting metrics for black holes. Okay, because this is physics. We want to try to get a lot of the math out of the way before we start talking about the physics, and the math is going to be somewhat of a prerequisite for all that physics that's to come. We're going to be talking about wormholes. We're going to be talking about black holes. It's going to be good stuff. So without further ado, let's get straight into the content. So again, make sure to hit that like and subscribe button. Go onto my Patreon page if you want to support the channel, where I have summary sheets and notes going up on my Patreon page if you want to take a look at those also. So we're talking about two derivations of the geodesic equation today. The whole idea here is that geodesics, the geodesic equation, geodesics are the paths that on a manifold, so say we have some manifold, and that manifold has some path on it, okay? And this path is the shortest path between two events, right? We're talking about space-time, so it's a four-dimensional manifold. And as we take some vector space at one point on the path, and we travel along that path, we can track vector changes along that path. And that's what, those changes are what the geodesic equation is going to get at, okay? And so let's go ahead and start. And we're going to start from the Einstein equivalence principle for this derivation. So this is going to be somewhat of an Einstein equivalence principle derivation, and then there's going to be a Lagrangian sort of principle derivation, or an Euler-Lagrange principle derivation. So this first derivation is really just the idea that acceleration is equal to free fall. This was the thing that sort of Einstein came to in his famous thought experiment in an elevator, where he figured that he wouldn't really be able to tell any difference if he was in an elevator falling from space, okay? And the idea here, again, is that that falling, right? So this is free fall. This is the free fall. If he was accelerating upwards, at 9.8 meters per second squared, this was his stipulation, that free fall is the same thing as an acceleration, okay? This was the revelation that enabled him to say, well, you know, if these are the same thing, then this person in the elevator therefore does not really experience an acceleration per se if he was in free fall. Okay, from his inertial perspective, acceleration would not be there. Okay, so his stipulation, again, just to belabor the point as much as I possibly can, is that free fall in some gravitational field is the same thing as accelerating, okay? And so, if there's no experience in this acceleration, in other words, you're just falling, okay? This upward acceleration is equal to free fall. You wouldn't feel anything, okay? So the idea here, again, I feel like I keep on belaboring the point, but the idea is it's going to be this right here, that the sort of the net acceleration, if you were to move upwards in this elevator again, at 9.8 meters per second squared, you wouldn't feel anything. Okay, so that's this right here. Okay. Okay, so let's go ahead and let's see here. I'll undo that, and then I will erase this. Okay, so now that we have this sort of in our minds, this Einstein equivalence principle in our minds, again, my apologies for the dog barking, we have, we can say this, right? So that the velocity of some space-time point can be given by this. This is just the product rule, right? So here's our dx mu d tau. We're saying dx mu is a function of some alternate set of coordinates, dx nu, and we can say that because of the product rule, we could say this. Okay. So if we take the double derivative of this, which is right here, then we take the derivative. We take the derivative of this, right? So we want the double derivative of this guy. That's the new coordinates times this, and then the derivative of this guy, which is right here, times this, which is right here. Okay. Then we invoke the Einstein equivalence principle. We say this guy is equal to 0, and then we get this. And then from here, you just move this to one side of the equation, which makes one side negative, the other side positive. Okay. We can see here that this is just, so this here is right here. We can use product rule again. Right, so here's our product rule. And what we can do here is, actually, wait, no, my bad. Right, so this right here is what we got to. Again, my apologies for the dog barking. We can multiply both sides, right? So we multiply both sides by this right here. Okay, and then we find that this is Kronecker delta. This here is our Christoffel symbols that we sort of beat up in the last video. And what we have now is, so I copied it up here, is this guy. And this is the geodesic equation, right? This here, I just now, let's see, did I make any changes? Yeah, I just swapped these two guys behind our Christoffel symbols. And this is the geodesic equation as you commonly see it. And ultimately it came from the idea here that this equals 0. If it didn't equal 0, this was the Einstein equivalence principle. If it didn't equal 0, then we wouldn't have come to the geodesic equation. Okay, so simply put, is that the Einstein equivalence principle naturally gives us geodesics. Okay, in some sense, you could say a geodesic is really just the statement made when Einstein made his principle of equivalence. Okay, what is this? When we look at this equation, this means that we have some acceleration on one side of the equation, or we have on this side of the equation, right? We have acceleration. On this side, we have velocity squared, right, and then some constants. So, really, what's being said here is that the velocity is given by a vector in the tangent space. Acceleration is therefore equivalent to the square of that times some constant. This constant, again, is given to us by our Christoffel symbols. Okay. And recall that if the velocity vector is hyperbolically related to the acceleration, this is given to us by special relativity. We talked about this in our first video. Then we have these two guys right here. These two. Then we have these two things that we made. Also, we made these stipulations in our first video also, where we talked about vectors along some geodesic. Here's the geodesic. We have a tangent vector. We were able to show, here's our light cone. there's our light cone. In one case, we have our time-like vectors. Then we have our space-like. And then what we actually haven't covered yet is our null vectors, right? So null vectors, these guys are going to be those that are traveled by particles of light, right? So light travels at these horizons on the light cone, and vectors along those are called null vectors. Okay, and so we can. So here's that image, right? So I actually put that image in here, sort of more on a manifold perspective, where we have our geodesic, okay, traveling in our manifold. We have velocity vectors, right, that are tangent to our geodesic, and those again are time-like, right? Those are time-like. And then we have acceleration vectors, which are space-like. And then we have our geodesic right here, right? So our time-like vectors or velocity vectors are always going to be tangent to our geodesic, because the geodesic describes positions. Velocity is the derivative of position with respect to some parameter, usually time, and or it is with respect to time, right? And so those are going to be tangent. And then the acceleration, well, we also said in special relativity that the acceleration dot product with the velocity equals 0. And that was something we said earlier also. And so these two guys have to be orthogonal. Here's our light cone, and then our null vectors are these guys, right? Okay. So that is our derivation of the geodesic using Einstein's equivalence principle. Now I want to go a little bit more advanced and talk about the Lagrangian approach to the geodesic. So we're going to start off with the Euler-Lagrange equations. I'm going to assume that you know this, okay? Because this could be a whole nother set of videos just talking about the Euler-Lagrange equations. So we're going to assume we know that. We're going to multiply both sides by 2 times the Lagrangian. When we do that, we get this. And then we can get from here to here by looking at this side part here, right? So here's our equation. And we want to take a look at this guy right here. This right here. So we're putting it right here. And we could say here that the derivative of this squared, well, that 2 is going to be brought over. Here's our Lagrangian. Here is then the derivative, right? So this whole thing is just chain rule, right? So this here is chain rule. This here is going to be the just splitting things apart, right? So we take the derivative with respect to this parameter. Again, I don't really explain what this parameter is, but this shows up in the Euler-Lagrange equations. This parameter right here. Typically, when we're talking classical mechanics, it's time. Okay. But anyways, let's get back to this. So with respect to, say, time, we'll call this time. We get to this point right here. Okay, again, so this is, again, just the product rule, right? Product rule here, product rule here. Okay. We move this guy to this side here, and we get all of this. The reason we do this is because we see this right here is the same thing as this right here. Okay? So we can replace this with all of this, and we get this, right? So distribute that negative sign. This becomes a positive. Bring this positive to the side of the equation. That becomes a negative. So this is our modified Euler-Lagrange Lagrange equation. All right. So now we are going to take a look at each one of these terms and then string it all together and see how the geodesic comes from these two guys, or comes from all of this. Okay. So our Lagrangian is going to be this guy. So our Lagrangian squared. So we're saying here that our Lagrangian is equal to minus g alpha beta x alpha x beta. Right, so that's what we're saying our Lagrangian is. This is going to be interesting to go into later. We're going to talk about Lagrangians and how they sort of fit into a broader scheme within general relativity. But needless to say, let's go ahead and get started. So if we want to find this guy here, that's this. We're going to take so we're taking the derivative of this, right? Because this is squared. So that's this right here. And we can say, well, we get this guy, oops, we have this guy right here, and then these two guys, right? And these two guys are, so the argument here is that these are going to go to 0. These guys are going to go to 0 because if we're talking about an inertial reference frame, so these guys are constants, so any derivative of them with respect to this parameter is going to be 0. Another argument you can make is by saying that these are, so if we're talking about the Einstein equivalence principle, again, if we're talking about the Einstein equivalence principle, if this is 0, right, so this here must have been a constant, right, if that was 0. So again, so you're taking the derivative of what was this is a derivative right here, okay? So you're taking the derivative of something, this is the acceleration, right? This is the Einstein equivalence principle. And so we get this guy right here. So I'll just write this down. The argument here is the Einstein equivalence principle. All right. Okay, so now we want to take a look at the second term. This is the second term. And we have this, right? So we're taking the derivative twice, first with respect to the canonical momenta, right? So that's this right here. And then time, that temporal parameter. And so when we do that, again, this time we're taking derivative dots, right? So these guys will not be going away, okay? And so we have this, okay? And when we get to this point right here, so to get from here to here, right, we just say this is just a Kronecker delta, right? Because these two guys are the same thing. So alpha mu, beta mu, and then we have this right here. So we have so we change. So because this is a Kronecker delta, we change our subscripts to match. And when we change the subscripts, we get this guy right here because these two guys are the same. And so when we take our derivative now, we're taking our derivative here with respect to this guy first. This guy's constant, and then we take the derivative here and multiply by this. Again, this is just the product rule. So from here to here is the product rule. And then we get to this point, right? So this guy is right here. And then all of this is going to be right, let's see, so this here, right, so this guy here, I'll put in purple. This guy here, if you recall, is dx d lambda. And so you can see, again, this is just chain rule, right? Because this guy is right here, this guy is right here. So you can see how that works. Okay? Then we go from here to go from here to here. We have, oh no, sorry, we're not going from here to here, right? So now we are dealing with this third term in our Lagrangian. All right. And then, so we get, so this is that third term. So we want to, here's our Lagrangian again. And we're not going to fill in the Lagrangian here quite yet, and we'll see why, because things are going to get simplified pretty quick. So when we flesh this guy out, this is a really big chain rule, right? Because we're taking, when you take the derivative of the square root, you get this inverse of the square root with this 1/2 factor, and then the derivative of the inside, which is this right here. But we found out that this is this, which was right. Let's see, this guy is right here, right? Because we're taking the derivative of all this, and that ended up being this. Okay, and so we get this. All right, so to go from here to here, we let's see here. There we had that 2. Bring the 2 out, and then this 2 and this 2 can also cancel. And so we get this guy right here. This negative also gets brought out here. So I'll just color code that like that. And then, my apologies for using this weird white color, but we're here now. So recall. So we want to recall now the action, right? So the action is just a functional of the Lagrangian, and the action being a functional of the Lagrangian says, well, using our fundamental theorem of calculus, we can take the derivative with respect to the parameter. Again, the parameter being, here's our geodesic, and we parameterize our geodesic in this way, and we're saying that the action is equal to that parameterization, and that's important. That's going to be important because the action we're saying the action is the is unit, not a unit, but here this parameter is given to us by the action, and when we want to minimize the action, we're minimizing the distance. Okay, that's the argument. Right? So we're going to see how that plays a role when we start putting pieces together here. But using the fundamental theorem of calculus, we get this. Okay, so if we take the double derivative now, we get this, and you can see now why we didn't do anything with this guy, right? Because now we can just plug in here our double derivative of the action, and this here is just this is 1 over L, right? Because this is this negative 1/2 here. Okay, so this is 1 over L, and L we said was the first derivative of our action right here. So we get this, and this guy here is that is this right here. So these two guys are equal. Piecing everything together now, so this was our modified Euler-Lagrange equation, here was our first term, here's that second term, and here was that third term. Now what we can do is we can say, here it is, right? So we just multiplied that negative out. So multiplied the negative out to these terms. Here it is. To get from here to here, well, this is the same. I'm going to put quotes right here because I'm not writing down this side of the equation. It's there, I'm just not writing it down quite yet. This guy right here, we can bring out the alpha delta. We get these two guys, right? Okay. And we're changing, because these are just dummy variables. Right, so the delta here, we're changing, or the beta, we're changing for delta. Okay? And then we get this guy here. Right, so this guy stays the same. This here, if you notice now, this is quite interesting, right? Because this guy stays the same, and this 2 is what's remedying all these 1/2, right? So, and then this guy here, again, the 2 is remedying the 1/2. This G mu alpha delta, we're going to split 2 ways, okay? So not really doing anything. All of this is just this. But what we can do now is we can swap dummy indices, these two guys, and when we do that, we have our Christoffel symbol. Okay, and then we're multiplying both sides of the equation by this inverse metric. So we get our inverse metric is going to clean up this guy. Okay, mu nu, mu alpha, and we're going to have some delta symbols in here, so we can change alpha to nu, and same thing here. This guy with all of this is our Christoffel symbol, and we have that 2 out in front. We have these guys right here, and then last but not least, we can change mu nu eta. So change our eta to nu, and then we have this guy right here, this right here, and then I did not put a 2 in here. But as you can see, the 2's are going to cancel, right? So 2's will cancel out. And what we have left is essentially our geodesic equation. You might ask, okay, what's going on here? Well, we said that the action, if we're trying to minimize the action, we're minimizing a distance. If we're minimizing it, that means the action can be measured as some constant or some distance. And so if S is equal to lambda, then S double dot, that's going to be equal to 0. Right? Because right off the bat, the S dot is equal to 0 because this is just a constant. So this is 0 also. So since this side is 0, then we get the geodesic equation. So we recovered the geodesic equation from this guy here, and we invoked a little bit of the Einstein equivalence principle when we talked over here about these guys. All right. And so this actually wasn't really the Einstein equivalence principle. I think I misspoke there. The idea being is that we have I'm not going to erase that. The idea, again, that's just going to take too much time to redraw. But the idea, again, being that this guy is the only guy recovered because these two guys this derivative here, this is not a function of, this dot here is not a function of these guys, so it goes to 0. All right. And so this is what we get, right? So this is the geodesic equation derived from using this as our Lagrangian. All right, so in one case we used the Einstein equivalence principle, and in the other case we proposed the Lagrangian and we were able to derive the geodesic. Okay, I want to make one final note about Lagrangians. So we said that this guy here, this was our Lagrangian, and from this guy we were able to derive our differential equations, which is our geodesic equation. The geodesic equation is our set of coupled differential equations that tell us something about the shortest distance, the shortest path that we want to pursue on a curve, some curved manifold. The question is now, okay, so this is a differential equation. The question becomes, are there other Lagrangians out there that can provide us other types of differential equations that are relevant in general relativity? The most important being the Einstein equation of motion. So this is going to be a huge area in what is going to be pursued in this video series, which is what Lagrangian are we going to propose here, and to be able to recover this equation. Okay, and what we're going to find, I'll just spoil it. What we're going to find is that the action, again, the action is a functional over four-dimensional manifold. We're going to have a square root of the determinant of the metric, right? So this, we need this. This is our volume element. We'll describe why this is a volume element. And then R. R is the Ricci or curvature scalar. And it tells us something about how volumes are, what volumes are like in curved spacetime, okay? Or how they deviate from flatness. So, deviation from flatness. We'll be able to recover the Einstein equations of motion. Einstein equations of motion with just putting R in there. What's super, super interesting is what we'll also get into, that since this is a scalar, this scalar is going to, well, it's invariant, which is kind of interesting, right? A scalar is invariant under different types of transformations. I noticed someone in one of my comments said that transformations were not everything in general relativity. I think they said something like curvature is everything in general relativity. Well, curvature is very, very important, and I'm not going to try to say it's not important, but the reason my thumbnail said that transformations are everything is because I think this, I'm sort of using this argument here to say, well, the scalar tells us something about curvature. Okay, scalar is something that is invariant under transformation. So this is sort of the argument, my argument, why I think transformations are everything, right? So we could have a debate about this until the cows come home, but the idea being is that this is invariant And so, are there other invariants out there that might tell us something about the interesting physics of spacetime? And what the answer is going to be is yes, right? So we have, say for example, the Kretschmann scalar, right? So this is our Ricci, or not our Ricci, our Riemann curvature tensors. Each one of these are Riemann curvature tensors. When we contract those guys, we get something interesting, which is the Kretschmann. See if I can spell this right. Kretschmann scalar. Another one is when we consider the dual of one of them, and then we contract. This is going to be our Chern Petrov, I think. Actually, don't quote me on this. I can't remember what the second name of this guy was. But we'll just call it the Chern scalar for right now. There's another name in here. I don't want to. I want to give the inventor or the founder of this scalar, the two founders of the scalar, some. I don't know what word I'm trying to find, but there's another name in here, right? It starts with a P. I can't remember exactly how to what it was, but that's a scalar also. And then we're going to have our A, B, C, D, R, A, B, C, D are duals of both of them, and this is going to be our Euler scalar. It's a scalar. But we're going to take a look at all these guys, right, and a lot more. And so, this is what I want to say about Lagrangians in general, for general relativity. So, with that being said, I realize this is somewhat of a long video. Make sure to hit that like and subscribe button. We covered everything we need to cover so far on Geodesics. And if you're interested in summary sheets, notes, again, go into my Patreon page, and I'll see you guys in the next video. Bye.